So this is the last part of the course. It's about testing. And last time we learned that there is a file model called stuck at file model. So for whatever reason, the file usually leads to a note in a circuit. Yes. Oh, sorry. Let me turn on the. Okay. So last time we learned this stuck at file model. So for whatever reasons of fault, a note in the circuit due to fault could stuck at zero, logic zero, or stuck at logic one. So this is so say this is a faulty note. It could always at one or always at zero, stuck at some logic level. And this is a very widely accepted file model. There are other models, but here in this course, we use this stuck at the file model. And okay, the topic for today is the automate test pattern generation method. So to test some fault, we could generate some pattern at the primary input in order to observe the fault at the output. The ATPG method we're going to talk about today assumes single stuck at fault model. Assume that there is only one fault, stuck at fault in the circuit. Although we assume only a single fault, but we will test all the nodes. We should test all the nodes in the circuit, stuck at 0 or stuck at 1. So usually in practice, the stuck at test not detect all or nearly all single stuck at the faults in a circuit. Every time we assume a single fault there, but we do many tests. We do all the single fault test for all the nodes. If we do this, it usually we can usually detect all or nearly all multiple stuck at faults and short faults. So although we assume a single fault at a time, but it can usually detect multiple faults in a circuit. Here, there are a number of methods for the automated test pattern generation. Here is the first one called the fault matrix method. This is a method more of a, here is a test vector. Let's find what faults, if any, it detects. A test vector is a sequence of text signal at the primary input. Let's consider this single logic gate, and it has three nodes, 2 inputs and 1 output, A, B, and Q. Its choose table, the normal choose table is shown here. It's AND gate. Output will be 1 when both inputs are 1. Now, say we apply this test signal 0, 0, 0, 1, 1, 0, 1, 1, all the combination for this. Now let's consider faults in the circuit. Okay. So every node can be faulty. So let's assume node A node A stuck at 0, always stuck up, and the output Q would be like this. If A is 0, stuck at 0, this is the AND gate. So Q will be always 0. So it's an output Q that you observe is always 0, no matter what test vector you apply to the input. And let's compare this output versus regular output Q. For the first three cases, you won't tell the difference, but you can tell the difference when test vector 4 is applied. The output Q normal fault-free output is 1, but faulty output is 0. So if we apply test vector 4, it can detect this fault, node A stuck at 0. Now let's consider stuck at 1 fault at node A, stuck at 1. So if we apply 0, 0, node well stuck at 1, so it's equivalent. We have 1, 0, so the output will be 0. But if we apply 0, 1, Okay. That's the first method for the fault detection. So we apply a test vector and to see what fault it can detect. It's straightforward. Now, the second method to detect fault is to automatically generate input pattern. It's called path sensitization method. This method is more of, here it's a fault. Let's try to find a test vector to detect it. Let me use this example. So suppose we wanted to detect a stuck at the 0 fault or node 6. Node 6 stuck at the 0. The symbol is SA0. We wanted to generate a test vector at the primary input at the node 1, 2, 3, 4 in order to detect this node at the primary outputs node 9 and node 10. Okay, since we are going to detect stuck at 0 fault at the node 6, so we should establish a logic 1, which is different from SA0, which is different from 0 at the node 6 for the fault-free circuit. We establish a 1 on node 6 for fault-free circuit. If it is fault-free, it should be 1. If it's faulty, then it's stuck at 0. It will, and this will make a difference at the output. So to generate a 1 at node 6, this 2 input OR gate, NOR gate, the input should be 0 and 0. 0 and 0. No, output is 1. We generate a 1 that is different from the faulty logic level at the node 6. And then we will try to establish a path so that this fault can be observed on the primary output, either node 9 or node 10. Okay, we wanted to propagate this 1 at node 6 to the output. Okay, say we wanted to pass this 1 to node 8 in the upper pass. Then this node 5 should be 0. If node 5 is 0, then node 6 can be passed to node 8 for an OR gate. If you set 1 to 0, 1 input to 0, then it's just the other is just a buffer, just a buffer. So we try to establish a 0 here, but this 0 is not possible because node 2 is already 0. This and this top AND gate output 5, node 5 will be always let me see. This is okay. Okay, this is okay. So node 5 can be 0. So then this node 6 is 1 will be passed to node 8. And to pass this logic 1 at node 8 to output 9, we should set the logic 1 at the input of this NAND gate. For NAND gate, you wanted to pass a signal, you should set one of the input as 1. But this is not possible because this pass from node 3, it will lead to node 7 to 0 all the time because node 3 is 0. So we cannot use node 9 to observe this fault. We have to use another path. Another path. So we wanted to try to pass this node 6 signal into primary output node 10. To pass that, we should set this node at the 2 input OR gate here input as 0 in order to pass the other input to the output 10 node 10. For this 0, then as node 3 is 0, so node 7 is always 0. So node 4 is don't care. So with this, we set node 2 and node 3 to 0, 0. And we can observe this faulty signal at node 10. Let me write it again. So we set it as 0, node 2 to 0, node 3 to 0, node 4 and 1, I don't care. So for a fault-free circuit, node 6 is 1, 7 is 0, so node 10 will be 1. But if node 6 has a fault, stuck at 0, and this 0 will be passed to node 10, 0. And this difference, if you are expecting a 1, but you detect a 0, then we know that there is a stuck 0 fault at node 6. So that's the concept. So we assume say there is a single fault at some point, and we try to derive an input vector in order to observe this fault at the primary output. But this method is this path sensitization method does not guarantee to find an input test vector, even if a test vector exists. So this algorithm sensitizes a single path to propagate a fault to the primary output. Does not guarantee to find a test vector, even if one does exist. Let's try. Let's look at this particular circuit. Assume node 6 has a stuck at the 0 fault. Now let's apply the previous method to see if we can find a test vector at the input to observe this fault. Now to node 6 is stuck at the 0, so we should generate 1 at the node 6 in contradiction to the fault. So node 2 and input 2 and input 3 should be both 0 to generate 1 at node 6. Now, suppose we wanted to propagate this signal from node 6 to node 9, and then finally to node 12. Okay, so we should set a 0 at node 1. So node 6 signal can be propagated to node 9, become a 0. in order to propagate noise signal from in order to propagate this signal from node 9 to node 12, we should set node 8, node 10, and node 11 to be 0. Right? Is this gate edge is a 4 input, no gate. We wanted to propagate one of input to the output, so we should set all the other inputs to 0. Okay, so to set node 10 to be 0, node 4 should be 1. Node 4 should be 1. So 1, 1 in the file 3 serial. Node 6 is 1, node 4 is 1. So output of F, gate F, be 0. And if with this image 0, 0, 0, 1, let's see this gate C. You see gate C is 0, 1. So this should be 0. 7 is 0 from this given input. And let's consider gate G. The other inputs connect to node 3, input 3. So it's 0, 0 input. It produces an output 1. Output 1 here. If not, node 11 is an input to gate H. Now one input is 1. This is all type or null type. If one input is 1, the output is determined. Output is always 0. So you cannot sensitize this faulty signal to the output. You cannot propagate this faulty signal to the output. It blocks at the gate edge. Because of this 1, it blocks the signal. So within this logic line, we cannot generate a test vector to observe a stuck at the 0 fault at the node 6. Actually, an input test vector exists. Say, if we have set all the input to 0, 1, 2, 3, 4, all the input to 0, then you can check that. Let's work on this. Node 7 would be 1. And node 11 would be 0. And node 5 would be 1. Node 8 would be 0. Right? And this is, so this faulty, this signal is passed from node 6 through gate E and F simultaneously. And because this is 0, this is 0, this signal, this two signal, they are the same. Node 9 and node 10, they have the same level, containing a fault information. It can be passed to node 12. So if we sensitize both paths from EH to the output or from FH to the output, so there are two paths for the fault information to propagate to the output. There are two passes. If we sensitize both of them simultaneously, we can observe this fault at the primary output. So you see a test vector does exist in this circuit. But this single pass sensitization method cannot find it, cannot find the input test vector. But there is a third method called D-algorithm, which guarantee to generate a test vector for a given fault if such a solution exists. If a solution exists, it guarantees to find the input test vector. This algorithm is called D-algorithm. It is developed by Rose at IBM in 1967. And let's see how the D-algorithm works. So it's here again, it assumes a single fault. We assign this D logic level D to represent a logic 1 in a fault-free circuit, but in a faulty circuit, it will be 0. This is so D is like 1 and 0, but for fault-free and faulty circuits, the value are different. D represents logic 1 in fault-free circuit, 0 in faulty circuit. And D bar represents logic 0 in a fault-free circuit, but opposite in a faulty circuit. Now there is a convention in this method for the nodes numbering and the gates numbering. So nodes on a circuit are numbered in such a way that the number on output nodes of a gate is higher than the numbers on the input nodes. Input node have a smaller number, output node has a greater number. And all primary input nodes are numbered consecutively, starting with number 1. And gates are numbered same as the number at its output. Say for this circuit, say for this gate, its output is 5, so we give a gate number 5 for this gate. So that's the some background. Now the procedure in this D algorithm is like this. First, assign D value to the given fault. Then set up input to develop this fault. Step 3 is set up a activity vector A, which contains the gate's name, which have D value at the inputs. And within this vector A, we take the gate with the smallest number. Start with the smallest one. Then set our input to propagate the D value on this gate. Step 6 is go back to step 3 to do it again, but it will stop as soon as a D or D bar value appears at the primary output. And the test vector will be whatever is set up at the input. Let's use the same circuit to illustrate this D algorithm. Now, so we have stuck at the file at node 6. So we assign a file D here, a symbol D. Now, step 2 is to set up logic 1 at the 6, set up D. So 2 and 3 should be 0. Now in step 3, we have activity vector A. Is vector contains the gate information. So here the vector is 9 and 10. This is gate 9. This gate, gate 10, they contain D as one of its input. So that's activity vector. Now let's pick the smallest number in this vector. It's gate 9 here. And we want to propagate this D to its output. So in order to propagate D to the output, it will become D bar. So node 0, node 1, input 1 should be set to 0. Node 1 should be 0 in order to propagate this D from 6 to 9. Now we update the activity vector A. Now this vector 12, this gate 12 and gate 10 contains a D or D bar as its input. Next, we look at this vector. Pick the smallest gate, which is this gate 10, F here. Gate 10. In order to propagate this to from node 6 to 10, we should set node 4 to 0. So this will be D bar. So propagate. And again, updated this activity vector. Only H, only gate 12 contains this contains D or D bar as at its input. Now we need to propagate the signal from this gate to the output. To propagate this, we should set node 0, node 8 to 0, node 11 to 0 for this node gate. And then fortunately, this is okay if we set node 1 to 0. Node 8 will be 0. And node 7 here is 1. And this is 0. So node 11 is 1. So through this algorithm, we can find an input vector that can test this fault at node 6. So that's it. This method, D algorithm, guarantees to find a test vector if it does exist. You see here, it allows more than one pass to propagate a gate. And the problem with the previous method is that we only consider single pass in the propagation. We set this to 0, but this is not necessary. Okay. Okay, I think that's all the content for today. Any questions? This is about automatic test vector generations. You should know the concept here. But in the actual test, such kind of input test method is generated automatically, as the name suggests. You write a program to generate this one. Here is we only look at one node, one file at a time, but you can also find the file, write a test vector, write the program to find a file at other nodes, and you have many test vectors. And through this, you can find all, if not all, then almost all fault in the circuit. Okay. So that's all for today. I've made an announcement in the Blackboard. Tomorrow's tutorial, I invited a professional IC designer to give you a guest lecture. I hope you can attend. He will explain the ASIC design in the actual in the real world. Okay. Okay, so that's all for today. Thank you for coming.